In section 7.1, we're going to use the fundamental trigonometric identities to solve various trig problems, find the trig functions of various angles, the ratios. So before we get started, I'd like to review what fundamental identities we're going to use. And those identities are going to be the definitions. For example, opposite over adjacent. If it's unit circle, it would be y. For sine, we're going to use our quotient identities. Our Pythagorean identities. Our cofunction identities. And the even/odd identities. And an identity is something that's true every single time you put a valid value in for your variable. So that means if I start out with something that's true, I'm going to end up with something that's true. And there is no really new instruction except for doing example problems actually using the identities. The first problem says the sine of pi halves minus x equals 12 thirds. And then the sine of x is negative. And for these problems, they want the values of all 6 trig functions. So the identity I'm going to use is the cofunction identity of sine, which says the sine of a complement is equal to the cosine of a function. So if the sine of pi halves minus x is 12 thirds, I know that the cosine of x is equal to 12 thirteenths, not 12 thirds, is 12 thirteenths. From this point, I can now use my Pythagorean identities in order to find out what sine is. Remember, sine is negative. We know that cosine squared of an angle plus the sine squared of an angle is equal to 1. Well, cosine squared is 12 thirteenths. So 12 thirteenths plus sine squared is equal to 1. 12 thirteenths, not 12 thirteenths, I'm going to subtract the 12 thirteenths from both sides. So I get sine squared is equal to 1 minus 12 thirteenths. 13 thirteenths minus 12 thirteenths is 1 13th. So sine squared of x is equal to 1 13th. Now take the roots, and I get sine of x is equal to plus or minus the square root of 1 13th, which is equal to plus or minus the square root of 13 over 13. However, we can go back up to our original conditions that said the sine of x is negative, and I can get rid of the positives in my plus or minus. So I now have 2 of my trig functions. I have cosine and I have sine. To come up with the remaining trig functions, we are going to use our definitions. Oh, I forgot one set of identities, our reciprocal identities. And be able to come up with the rest. So the easy ones are going to be the reciprocal identity for cosine, and that would be that the secant of x is 13 twelfths. The reciprocal identity for sine is cosecant. So cosecant of x is equal to the square root of 13, and that's negative. Tangent is sine over cosine. So I have negative root 13 over 13 over 12 over 13. So I have the tangent of x is equal to negative root 13 over 13 over 12 over 13. The 13s cancel, and I get tangent is negative square root of 13 twelfths. And then the final trig function is cotangent, And that is the reciprocal of this one, so that would be negative 12 root 13 over 13. Notice I showed no work of rationalizing the denominator here, because we should all get into the habit of, hey, if I'm flipping this over, I'm going to get a square root of the 13 on the bottom. The way I get rid of that square root of 13 is multiply top and bottom by the square root of 13, and then the bottom is just going to end up being the 13. So you need to get in the habit of just being able to immediately convert, if the denominator is a root, being able to immediately rationalize that denominator. The second one says that the cosecant of an angle is negative 5, and that the cosine of the angle is negative. So if I'm given the option of using the first Pythagorean identity, cosine squared plus sine squared is 1, I will use that. So the first thing that I'm going to do is I'm going to use the reciprocal identity for cosecant and figure out what sine is. So I know that sine of my angle is equal to the reciprocal of negative 5, which is negative 1/5. And now I'm going to use my Pythagorean identity to solve to figure out what cosine is. So I get cosine squared theta plus sine squared theta, which is negative 1/5 squared, is equal to 1. Well, 1/5 squared is 1/25. So I have cosine squared theta equals plus 1/25 is equal to 1. Subtract the 1/25 from both sides. I get cosine squared theta is equal to 24/25. Take the square roots, and again, I look up here, I'm only going to take the negative square root. So I get cosine theta is equal to negative square root of 24 over 25. The square root of 25 is 5. The square root of 24 is 2 root 6. And I have a negative sign in front of it. And the way I got the 2 root 6, 24 is 4 times 6. Square root of 4 is 2 times the square root of 6. Now that I have my sine, my cosine, and my cosecant, I can use our identities to come up with the remaining ones. So I'm going to use the reciprocal identity for cosine and get that secant of theta is equal to negative. And what I'm going to do is I'm going to flip this one over, or I can flip this one over. So that would be negative 5 over 2 square root of 6. I'll actually do this one for you. Square root of 6 on the bottom. Okay, then what I have to do is multiply top and bottom by the square root of 6. Okay, square root of 6 times the square root of 6 is 6. 6 times 2 is 12. So I have 5 root 6 over 12. So that was secant of theta. And my last two, again, are going to be tangent and cotangent. Tangent is sine over cosine, and let's just do a quick little analysis here. I have a negative and a negative. Those are going to cancel to become a positive. I have a 5 and a 5. Those are going to cancel and become 1. So I'm going to end up with 1 over 2 root 6, which is the square root of 6 over 12. My cotangent is the reciprocal of this. I'm not going to take the reciprocal of my rationalized version. I'm going to take the reciprocal of the unrationalized version because that'll rationalize it for me. And that's just going to give me 2 root 6. So again, most of the work here is just coming up with, for me, it's coming up with the sine and cosine and going from there. Okay, next one. They tell me that tangent is undefined and that the sine is positive. Okay, the tangent is undefined when the denominator of the tangent function is 0. So I know that the tangent of theta is equal to sine of theta over 0. And I want to know when is the sine of theta 0. When sine is positive. Well, for that, I need to draw the unit circle. Well, that's cosine of theta. I know cosine of theta is 0 here and 0 there. Okay? It's 0 anywhere along the x-axis. Okay? So, actually, wrong. Cosine is 0 here, anywhere along the y-axis. So I can pick any point along that y-axis, and I'm going to pick the unit circle point where this is 0, 1. Okay, I could have also picked 0, 1/2. I could have picked 0, 1/3. I could have picked any positive y, which was any number in this area for my y, where x is 0 along the y-axis. I just picked the easy one. So we already know that tangent's undefined. And from this information, I know that cosine is 0. And I can now pick, the reason why I'm using the unit circle definitions is I could also use the trig of any angle definitions where it's y over r for sine. But if r is 1, y over r is just going to be y over 1, which is just y, which makes the definitions easy. So the sine of 0 is 1. The reciprocal identities, I get that the secant of theta is 1 over 0, which is undefined. I get the cosecant of theta, which is 1 over 1, which is 1. And then the last one I have is I'm going to do cosine over sine for cotangent. I get 0 over 1, which is 0. Every one of these problems, I could have used the trig of any angle approach. Okay, the purpose of these problems is to show you that, hey, there are multiple ways to solve the problem. I will say that I did need one of my identities for the cofunction, where the sine of a complement is equal to the cofunction of the original angle. You could have used trig of any angle. Once you had that cosine was 12/13, you could have drawn a triangle that had its adjacent side of 12, its hypotenuse of 13, and from that point, memorized right triangle, you knew this was 5. However, you knew that the y was going to be negative, so I would have drawn my final angle in a quadrant 4 orientation, where this is 5, 12, 13, and from there you could use the trig definitions of any angle to come up with the same answers that we came up with here. So the next section of 7.1, we are going to factor trigonometric expressions using some of our identities. So give me a second to erase the board, then I will get to our next section. The emphasis of these next group of example problems is to show you that anything that I can do with a real number, I can also do with a trig function. That's part of it, because the sine of an angle, the cosine of an angle, the trig functions of an angle are ratios, and those ratios give us real numbers. So we just need to remember back to basic algebra, and that's what we're going to be doing for these problems. The first example says to factor and then simplify sine squared of x times secant squared of x minus sine squared of x. So what I'm going to do is I'm going to pull out the greatest common factor, which is sine squared of x. Sine squared, secant squared divided by sine squared is secant squared of x, minus sine squared over sine squared is 1. And this is one of the forms of the Pythagorean identity with secants and tangents. On a sidebar, that Pythagorean identity is that tangent squared of an angle plus 1 is equal to secant squared. So if I subtract 1 from both sides, I get that secant squared minus 1 is tangent squared of x. So I get sine squared of x times tangent squared of x. And that's pretty much as simple as you can get it. I can also rewrite tangent as tangent squared is sine squared over cosine squared. So another possible answer would be sine to the fourth of x over cosine squared of x. And personally, this form would be more beneficial for you. If you can get it into the fundamental trig functions of sine and cosine as your final answer, that more than likely would be the answer that's going to be more useful for you if you're going to take classes beyond college trigonometry. My second example, I have, well, let's just look at this. If you would have saw x minus 2 over x squared minus 4, hopefully most of you would have recognized that x squared minus 4 is equal to x plus 2 times x minus 2. The same thing holds true here. The cosine of x squared minus 4, I'm going to copy the numerator, is equal to the cosine of x plus 2 times the cosine of x minus 2. Notice here that the cosine of x minus 2's cancel, and your final answer is 1 over the cosine of x minus 2. Note that this is not, I'm going to emphasize again, this is not to the secant of x minus 2. That's equal to the secant of x, but you can't just flip that part over also. So do not go beyond that part right there. Again, once you get it into one of the fundamental trig functions, sines and cosines, or if you get a single trig function like secant, cosecant, tangent, or cotangent, I would stop. The last problem again takes us back to our algebra, where I want to factor this. That's again part of the directions is to factor it and then simplify if possible. Well, I have a cubic that has 4 terms, and we saw in Algebra 2 that if you had a cubic with 4 terms, you could try to factor it by grouping. You put a parentheses around the first 2, parentheses around the last 2, a plus sign in between the 2. You figure out what the common factor is in the first group. Common factor between secant cubed and secant squared is secant squared x. You find the common factor of the last group, which is 1, but since there's a negative sign here, we're going to make that factor a negative 1. This is my first factor, which is secant squared x minus 1. And my second factor, I'm just going to do the division. I can do the division either the left set of parentheses or the right set of parentheses. The right set seems easier. I'm going to do that one and then check my work with the second. Negative secant x divided by negative 1 is secant x. Positive 1 divided by a negative 1 is a minus 1. But I still am not completely factored because this is a difference of squares. So I end up with secant x plus 1 times secant x minus 1 from the difference of squares, times another secant x minus 1. So I'm just going to put that one squared. This right here is where I would stop. Please note that on my previous problem, when I had secant squared x minus 1, I turned it into a tangent. Okay? So this is an answer. To me, this is a reasonable answer because this is something that I'm going to be able to work with as an equation. What I want to do now is I'm going to take this form right here and I'm going to turn the left-hand part into tangent squared x, and let's see where that one goes to. So that gives me tangent squared x is times secant x minus 1. Well, what I'm going to do now is I'm going to turn this into sines and cosines. I'm going to turn this into sines and cosines, and let's see what we get for a final answer. So I have sine squared x over cosine squared x. That's going to be multiplied times both of these. Well, secant is 1 over cosine. Okay, and again, I get the tangent squared x. Notice here you end up with sine squared x over cosine cubed x minus tangent squared x. And to me, this is just this is not any simpler than this is. To me, this actually has meaning. You should remember that when you were factoring something in algebra, you were coming up with things so that if this was equal to 0 on the right-hand side, you would set each of these equal to 0, and those would give you your x-intercepts. We're going to be able to do the same thing in our next sections. We're going to be able to find the x-intercepts of the graph of this function. And notice here, same rule applies. If an x-intercept has an even multiplicity, the graph is going to touch that x-intercept instead of crossing at that x-intercept. So this form right here actually provides us meaning, where this one, keep on going and digging into the ground, you can get all sorts of different forms. That's what the directions of the practice problems that you're going to do say. Try to keep it in something that's meaningful for you. So I'm going to do 2 more groups of examples. Let me pause, erase, and then we'll get going. The next group of problems is just going to show you various other techniques that you can use to simplify our trigonometric expressions. The first one is example 1. It says 6 cosine squared x plus 5 cosine x minus 6. This is very analogous to having the same problem that looks like 6x squared plus 5x minus 6. Or if I wanted to simplify that, basically I want to factor that. Okay, and if I would factor this one right here is, we're going to factor it by grouping. So I need 2 numbers that multiply to negative 36. That's the 6 times the negative 6 that add to 5. So factors of 6 are 2 and 3. Factors of 6 are 2 and 3. And let's see, what do I have here? I have a positive 9 and a negative 4. That will be my 2 numbers that I have. So I'm going to put the either number with either one. I am going to put the negative with the negative just to get rid of that. So factoring by grouping, I copy the first term. I'm going to split this term up into 2 parts. I'm going to put a plus 9 cosine x minus 4 cosine x. And then I copy the last part. And now we're like one of our previous examples, where I put parentheses around the first 2, parentheses around the last 2, plus sign in between the 2. Factor out the greatest common factor of each group. Greatest common factor between 6 and 9 is 3. Greatest common factor between cosine and cosine squared is cosine x. Greatest common factor between 4 and 6 is 2, but because the first term is negative, I'm going to make it a negative 2. So my first term is just copying these two down in parentheses. And my second term would be to do the division. 6 divided by 3 is 2. Cosine squared divided by cosine is cosine. 9 divided by 3 is 3. And cosine divided by cosine is 1. Check the math. Negative 4 divided by negative 2 is 2, cosine x. Negative 6 divided by negative 2 is positive 3. So I want you to recognize that if you see a pattern that if you were to replace the trig function with just an x and you would be able to factor it, that's the method that you are going to use to factor it. Okay? Some of you don't like to do the factoring by grouping here. For example, I could have just said that, hey, u is equal to cosine of x. Then I could have rewritten my original problem as 6u squared plus 5u minus 6, gone through the process of factoring by grouping. So that would have been 6u squared plus 9u minus 4u minus 6. Again, I just used the same numbers I had up here. Do the grouping process. And I would have had 3u minus 2 times 2u plus 3. And my last step, since my problem did not have u to begin with, I could have put the cosine x everywhere that there was a u, and that would have resulted back into what I did using the trig functions as they were originally in there. So having the trig functions in there when you are doing your factoring process confuses you, give yourself something that you can substitute in for the trig function. My recommendation is not to use x because we've already got an x here. But turn it into an Algebra 2 problem or a college algebra problem, do the factoring, and then at the very end go back and resubstitute back in for whatever you used as your substitution variable. This next example, it says sine squared x plus 3 cosine x plus 3. I can't just directly factor that one because I have sines and cosines. So what I want to do is use one of my fundamental identities to turn either this cosine into sines or these sine squareds into cosines. Well, I don't have anything directly to turn cosines into sines, but I do have something that will turn sine squareds into cosine squareds. And that is that sine squared of x is equal to 1 minus the cosine squared of x. That's one of our Pythagorean identities. So what I'm going to do is where sine squared is, replace it with 1 minus cosine squared. So that gives me 1 minus cosine squared x plus 3 cosine x plus 3. What I'm going to do now is I'm going to combine like terms. I get 1 plus 3. That gives me negative cosine squared x plus 3 cosine x plus 4. We really didn't factor things when we had a negative in front of the whole thing. So what I'm going to do is I'm going to pull a negative out of every term to make it easier for you to recognize what this is. So if I take a negative out of this, it's now a positive. Then I have minus 3 cosine x plus 4. I am now going to do a u substitution just to show you another u substitution. I'm going to say u is cosine x. So I now have the following problem to factor. U squared minus 3u plus 4. Two numbers that multiply to 4 that add to negative 3. That would be negative 4 and a positive 1. So I get minus u minus 4 times u plus 1. Put my cosine of x back where u was, and I get negative cosine x minus 4 times cosine x plus 1. Again, you did not have to do this u substitution if you directly saw that, hey, I need two numbers that multiply to 4 that add to negative 3 and just done the factoring without doing the substitution. Okay, last problem I'm going to do on this group before I would do the last set of examples is a multiplication problem that after I multiply, I'm going to simplify using fundamental identities. I have a number plus a number times a number minus the same number. That's a difference of square pattern. So it means we always square the first term minus square the last term. So my problem is 2 cosecant x plus 2 times 2 cosecant x minus 2. So I'm going to square the first term. Cosecant x squared is 4 cosecant squared x. The last term is 2 squared is 4, and I put a minus sign in between the two. Notice I have a common factor, so I'm going to pull that out. That gives me 4 times cosecant squared x minus 1. Cosecant squared x minus 1 is part of, actually, is it one of our trig identities? So let's look at our Pythagorean identities. I have sine squared x plus cosine squared x equals 1. I have tangent squared x plus 1 equals secant squared x. And I have cotangent squared x plus 1 equals cosecant. You need to have these memorized or be able to come up with them rapidly. Notice here that if I subtract 1 from both sides of the last one, subtract 1 here, subtract 1 here, I get cotangent x is equal to cosecant squared x minus 1. So where this is up here, I'm going to replace it with cotangent squared x. So the final answer would be 4 cotangent squared x. And we are done. So again, we're using algebra. All the rules that we used for algebra, we are doing the algebra on the problem, and at the very end, we are simplifying it down to a single trig function or part of our fundamental trig functions. Again, we want it meaningful because more than likely we are going to use this type of process to solve trigonometric equations, and solving those equations we're going to want to find x-intercepts. So right here, I would be able to find the x-intercept. I would want to know when cotangent is 0. Here, I'd want to know when cosine is 4 or when cosine is negative 1. Hey, it can never be 4, but I know when it's negative 1. Here, I would want to know when cosine is 2/3 or when cosine is negative 3/2. Well, cosine can never be negative 3/2, so I only want to know when cosine is 2/3. That's where these things are going to be meaningful for us, is when we get to the next section, solving equations. So one more group of examples, and we'll be done with 7.1. So this is our last group of examples. Again, the directions for these are to use fundamental identities to simplify. And again, there may be more than one correct answer. And the directions for the last one is to rewrite it so it does not have a fraction. So again, I'm going to look at these problems, and I'm going to immediately recognize on the first one that a number times its reciprocal is always 1. So my first step is tangent times cotangent is 1 over secant. Well, I know what 1 over secant is. That is cosine of theta. So if you get a final answer that says tangent times cotangent over secant, and that means you're going to have to plug theta into 3 different things. Well, or you could just plug it in once into the cosine function. The second one, I've got 4 different trig functions I have to deal with. So the first thing I'm going to do is I'm going to rewrite every one of them as part of the fundamental trig functions, sines and cosines, and see what I have. Well, cotangent is cosine over sine times sine. Tangent is sine over cosine times cosine. And you should notice that the cosines cancel here, sines cancel here, and the final answer is going to be the cosine of u plus the sine of u. So again, I turn them into all sines and cosines, then simplified from there. The next problem is an addition problem. It's actually an addition problem of fractions. In order to add fractions, I have to have a common denominator. Well, the common denominator here is going to be 1 plus sine x times cosine x. So I need to multiply the left side times cosine x over cosine x. I need to multiply the right-hand side times 1 plus sine x over 1 plus sine x. And let's see what we get for our work. I am not going to multiply these things through. I'm just going to leave them in form in the denominator. So the denominator is cosine of x times 1 plus the sine of x. On the top, I get cosine x times cosine x, which is cosine squared x. Okay, this is a binomial squared, so it would be the first term squared, plus 2 times the product, which would be 2 sine of x, plus the last term squared, which is sine squared of x. Now, what I have here is I recognize that cosine squared x plus sine squared x is one of my Pythagorean identities. That is 1. This is equal to 1. 1 plus 1 is 2. So, that is going to be 2 plus 2 sine of x or cosine times 1 plus the sine of x. I can factor a 2 out of everything here. That's going to give me 2, 1 plus sine over cosine x times 1 plus sine of x. My sine of x's cancel. I now have 2 over cosine. Something over cosine is that number times secant. So my final answer is going to be 2 secant x. So again, it's just like Algebra 2 or college algebra. If you have a fraction, you find what the lowest common denominator is, you multiply by what's going to give you that lowest common denominator, and then you simplify. The last example is 5 over the tangent of x plus the secant of x. And it says to rewrite this without fractions. So what I want you to realize that this is actually a complex fraction. It's a fraction with fractions inside of it. And the way you can see that is actually rewrite these two, tangent of x and secant of x, as fractions. I'm going to rewrite this one as a fraction also. It's the fraction 5 over 1. Tangent is sine over cosine. Secant is 1 over cosine. Next thing I'm going to recognize is that I have my complex fraction. In order to get rid of a complex fraction, you multiply every little fraction by the LCD of the little fractions. Well, the LCD of 1, cosine x, and cosine x is cosine x. So I'm going to multiply every little fraction by cosine x. And you should notice now that all of my little fractions are gone. And let's see what we have. We have 5 cosine x over sine x plus 1. And I did not get to what I wanted to. Okay, so you notice that this is just another way to write that. Again, it wanted us to get rid of fractions. So let's see another way. Let's look at our fundamental identities. Let's see what squaring that thing would do. That would give me, or difference of squared on that. So I'd end up with tangent squared minus secant squared over 5 tan x minus secant x. There we go. So what I did here is I multiplied numerator and denominator by tan x minus secant x. This is a difference of square pattern. First term squared minus last term squared. This one right here, we have a number for. We know that, I'm going to write it down here, that tangent squared x plus 1 is equal to secant squared x. If I subtract the secant squared x from both sides and subtract 1 from both sides, I get tangent squared x minus secant squared x equals negative 1. So this term right here is just a negative, and I would get my final answer as negative 5 times the tangent of x minus the secant of x. Please note that the first way I did it is my first response on always going to solve these problems. Hey, I see a complex fraction. How can I get rid of a complex fraction? Once I realized that that did not work, I'm looking for other things that I can do. Hey, if you got a number plus a number, always think about multiplying by its conjugate. What am I going to get when I multiply by its conjugate? I'm going to get a difference of squares pattern. Is that difference of squares pattern one of my fundamental identities? Okay? And if you've got tangent and secants, then yes, it will be. If you've got cosecants and cotangents, it will be. And if you have sines and cosines, it will be. So those are the things that you want to look at when you're going about solving these problems. How can I turn it into something that I can simplify? Again, this is a valid answer, but it's not the one they were looking for because this is still a fraction. Now, I could have then taken this one, multiplied it by its conjugate, and I would have ended up with sine squared minus 1, which is negative cosine squared, which would have been a negative. It would have been negative 5 cosine x times sine minus 1. Again, that would have been without a fraction, and it's a valid answer without a fraction. So there are two ways that I could have got valid answers without fractions, but just think through your process. The only way to get better at these is to actually practice them over and over and over again. Thank you.